Hello, my name is Rico, and welcome to my presentation on isolating GPU architectural features using ParallelismAwareMicrobenchmarks. In this presentation I will give a brief look into the research Stephen, Anna and myself have done on this subject. So why do we care about this subject? So every generation, extensive architectural changes are implemented in GPUs. These can range from core design to memory architecture to scheduling changes and even to special features such as tensor cores. But what's not clear is the effect these features have on performance. So what we are researching is how do we determine the impact and how do we apply these new features effectively. So how can the architectural differences between devices from different generations be evaluated and exploited? So I will be covering our evaluation methodology. I will give a brief architectural overview on GPUs. I will cover our results on the memory architecture. And finally I will give some concluding remarks. So our workflow for each architectural feature is the same. So we try to isolate the feature we're interested in using microbenchmarks. Then we try to parallelize the microbenchmark. And we also want to utilize a fine-grained timing method so we can uncover in more detail what happens on the GPU. So we will use 3 different generations of NVIDIA GPU. So we use Pascal, the GTX 1080 Ti from 2016, Turing, the RTX 2080 Ti from 2018, and Ampere, the A100 from 2020. So a brief architectural overview. So GPUs are highly parallel. They are made of SMs, global memory and L2 cache, and additional I/O, for instance, to communicate with the processor. So each SM actually contains the logic. So they contain load store units, the processing elements, in case of newer architectures, tensor cores, which accelerate matrix-matrix multiplication, and the L1 texture cache and shared memory. So how do we program this? We use CUDA, which is NVIDIA's own programming model. In concept, it's very similar to that of the GPU, where each execution kernel consists of blocks, which can be compared to SMs. Then each blocks consist of individual warps, and each warp consists of 32 threads running in lockstep, meaning they execute the same instruction at the same time. So CUDA also allows us relatively low access to the hardware, so we can query which SM a thread is running on, we can read hardware timers for accurate timing, and we can use the shared memory to quickly store our timings without interfering too much with the processing. So our results for the memory architecture. So first we note that there are different L1 cache architectures between Pascal and Turing and Ampere. So on Pascal the texture and L1 cache is combined, whereas on Turing and Ampere the shared memory and L1 cache is combined, which according to NVIDIA should lead to lower latency. We also know there are different L2 sizes and different main memory speeds, but for our research we limit ourselves to L1. So we base our initial microbenchmarks on existing papers. We note that these microbenchmarks utilize very little parallelism, so we try to extend them to use multiple warps or multiple blocks. And we use the high accuracy timers to uncover scheduling characteristics. So first we start with latency and then we go to bandwidth. So for latency, we base it on an existing pointer change method, where a single thread uses strided accesses on a buffer. Each access, the time is measured that is taken for the access, and then we gradually increase the buffer size until the L1 misses start to increase. So using this method we can find characteristics such as the L1 cache size, the cache hit latency, and perhaps even an indication of a fixing strategy. So what did we find? So on our Pascal card, which should have 48 kilobytes of L1 cache, we actually see that on 24 kilobytes it already starts to show an increase in misses, which is quite curious. So on Turing this is 25 kilobytes, and on Ampere it actually is lower at 22 kilobytes. But we do see that the increase of average access time is smaller on Ampere, meaning that at the higher buffer sizes the latency is actually lower on Ampere slightly. So now we want to parallelize this benchmark, so we extend this microbenchmark to utilize multiple warps per block. So this ensures they run on the same SM, but we do have some level of parallelism. We ensure one active thread per warp, and each thread accesses the same data. So in an ideal world, we would see no performance impact whatsoever on this, because all of the data can be reused. And as well, we ensure that the buffer is small enough to fit in L1. So first for a baseline. So on Pascal, running this test takes roughly 25,000 cycles. But when we run 232 threads, it actually increases to almost 50,000 cycles. So we can see there's quite a high level of contention between different threads. And we also see that once some threads start finishing, the other threads more in the red color start to increase in speed, visible by this bend. So how does this compare to Turing and Ampere? So again, we have a baseline where they both roughly take 25,000 cycles. And we see that the impact from contention is actually much smaller. So on Ampere this is even less than 5,000 cycles. So we change our experiment now to use multiple blocks instead of multiple warps. And as well we let our blocks execute on different data. So what this will tell us is what sort of contention we can see on the L1 cache when different blocks are utilizing the same SM. So for a baseline, again, we have roughly 100 cycle latency on Pascal. But then when we add a second block, actually nothing happens despite our expectations of contention here. But when we add a third block, we actually do see some contention. So one block is still at around 100 cycles, but the other two blocks clearly show contention and a lot of L1 misses. So compared to Turing and Ampere, again, we have a baseline of just below 100 cycles. But here, when we introduce a second block, we already start to see a lot of contention and L1 misses. So what do we find on these latency measurements? So first off, Pascal has a higher hit latency. So this coincides with FVD's claim that the architecture is improved on Turing and Ampere. And as well, we can see that Turing and Ampere have some sort of least recently used eviction scheme. So looking at the contention, we see that every new architecture, this seems to become a smaller issue where there's less contention. And when we ran multiple blocks in the SM, we actually note that Pascal has some sort of split SM design where in a single SM, the two halves cannot really interact with each other, which was also shown by our initial latency measurements where we only reached half of the reported cache size. And Turing and Ampere on the other hand show the behavior that we would expect. So moving on to bandwidth. So again, we base our approach on existing papers. Blocks consisting of multiple warps. Each warp accesses all elements in a buffer, and all buffers on an SM should fit in L1. So the existing method, we noted some discrepancies between the two papers. So they use different data types and they use different instructions. So instead we will use multiple data types and multiple instructions and keeping it the same across architectures. And as well we use timers on an SM to determining scheduling behavior. So for timing results, so here we see each color is a different block and each line is a different warp. So for our base result on Pascal, we see that this test takes roughly 15,000 cycles to complete. And when we add a second block, again, it takes roughly 15,000 cycles to complete. Again, showing some indication of the split SM design where the two halves cannot interact with each other. So when we run 4 blocks, we actually see that the first 2 blocks execute at the same time, and the second set of blocks also executes at the same time. So on Turing and Ampere, again we have a baseline. These are not comparable because the buffer sizes are different. So when we run 2 blocks, we actually see that on Turing only a single block can run at the same time, and on Ampere 2 blocks start at the same time, but only one is able to execute at the same time, indicating more resident threads on Ampere. So bringing us back to our main research question, so how can the architectural differences between devices from different generations be evaluated and exploited? So we made some interesting observations, so for instance the split SM design on Pascal, the new eviction policy on Turing and Ampere. We showed differences in level of contention, but this also leads us to some important takeaways. So we found that picking suitable parameters is very important for the performance you will achieve. So use a sensible block size to utilize cache and processing elements. Use a number of blocks equal to multiple of the number of SMs. And most importantly, make applications tunable based on architectural features. So don't hard-code kernel parameters. So thank you for listening. This was our presentation. For a more in-depth look into this subject, I recommend reading our paper. And thank you for listening.